It is my pleasure to welcome to Paul Christoph Thale from Bochum, who will speak to us about random cones. Christoph?
Yes, thanks a lot for the invitation to speak at your seminar about random cones at this very, very special German day. And since I had some conversation about this German day with Beatrice, I wanted to share also with you that this is a very special day for Germany because many historical events that took place in Germany took place at the 9th of November. For example, the proclamation of the first so-called Weimar Republic was the 9th of November. The Crystal Night, where the Nazis burned the synagogues and Jewish shops, that also took place at the 9th of November. But also lucky events like the fall of the Berlin Wall. This was also a 9th of November, but because there are good events and bad events, it's still not a holiday this day, a national holiday. It's just a usual day, but very important for Germany. But since we are here to do mathematics, I would like to start to introduce the model I would like to look at with you. So we are dealing with the d-dimensional sphere, and we imagine the d-dimensional sphere sitting in the d+1 dimensional Euclidean space Rd+1. And on the sphere, we just put uniform IID random points, U1 up to UN. These are n uniform random points on the sphere. And for each point, you construct the hyperplanes U1 perp to UN perp. And here you don't see the points, but in my picture, you just see these hyperplanes, and you see that these n random hyperplanes, they partition the ambient Euclidean space Rd+1 into random cones, right? You see here all these random cones that are glued together at the origin. And it's a very old result going back to Steiner for D equals 3, I guess, and Schläfli for all higher dimensions, that independently of everything, almost surely, this is a constant number of random cones, and this constant number I will denote by Cn d+1. So n is the number of hyperplanes you see, and d+1 is the dimension of this ambient space. And this number is given by 2 times sum from m equals 0 to d of these binomial coefficients. This is the number of polyhedral cones that you will almost surely see. And the concept we would like to study is a random cone. And so how do we get from this almost surely constant number of random cones to, let's say, a model of random cones? It's that you now select uniformly at random one of these random cones. And to honor the work of Schläfli, the Swiss mathematician, this random cone is called the Schläfli cone, or the random Schläfli cone. And in this talk, this random Schläfli cone will be denoted by Sn. It's just one of these random cones selected uniformly among the collection of all random cones. And this is the random Schläfli cone. And that's the object we would like to study. And well, we are not the first one who studied this model of random cones. It was this paper of Cover and Efron in the 1960s, where they computed the expected F vector of this random Schläfli cone, or equivalently, if you intersect this random cone, this random Schläfli cone with the unit sphere, you will see a spherical polytope. And equivalently, they computed the F vector of this spherical polytope, the expected F vector. And it's given by a quotient of these fancy numbers, C something, comma something, and well, a certain power of 2 and a binomial coefficient. And what they observed is, if
Just
you
a
let
question.
n, yeah, there's a question?
Yes, F vector is k-dimensional face, right?
Sorry?
F vector of a cone is k-dimensional face, am I right?
Yes.
Okay.
Yeah, so the fk of a cone is the number of k-dimensional faces of this cone, and fk of the spherical polytope is the number of spherical k faces of this polytope.
Thank you.
Yeah, so they computed this expected f vector of this random cone, or equivalently this spherical polytope, and they observed that if you let the number of hyperplanes tend to infinity, this converges, and it converges to 2 to the d minus k times d choose k. And well, what you see here is exactly the number of k-dimensional faces of the d-dimensional cube. And the paper ends with the following sentence. So they say that, loosely speaking, the expected cross-section of this random Schläfli cone Sn is a cube, right? So if you look at the cross-section of this cone, you will see a cube. That's what they claim, and well, what they prove is this statement here. I quoted. Well, we thought that, okay, this is true as long as you look at combinatorial parameters of this random cone, so especially the f vector. But our question was, is this also true if you look at the shape of this random cone? So what we would like to look at is the shape of this cone. And of course,
Christoph?
well, you have to make precise what you mean by the shape, of a cone. Beatrice.
Yes. The reason that they were looking at spherical polytopes, is it because the cones will be unbounded and the question wouldn't make sense otherwise? Or they also cover that version?
Makes sense. I mean, just if you look at the f vector of the cone, it's completely equivalent to looking at the f vector of the spherical polytope. It's the same.
Okay. Mm-hmm.
Yeah, it's completely the same thing. But it's you will see why maybe looking at the spherical polytopes is maybe more nice to work with, but it's completely equivalent. So as I said, we want to look at the shape of these random cones, of the cross sections of these cones. And first of all, we have to make precise what we understand by the shape of a cross section of a cone. And for this, we introduce the notion of a profile of a cone. And by the profile of a cone, we mean the following thing. So here you take this random Schläfli cone, and this random Schläfli cone cuts out the spherical polytope from the sphere. So this is the spherical polytope here. And in the spherical polytope, you can choose a uniform random point that I will denote by USN. So this is a uniform point in the spherical polytope. This is the white point here. And now you can look at the tangent space of the sphere at this white point. So this is this line here indicated by this line. And you can intersect the random cone by this tangent space at this random point. And this is what we call the profile of this cone, right? So this symbol means the tangent space at the uniform random point, and this red line here is the profile of this cone. So if this is a two-dimensional cone, this is a one-dimensional profile, and in general, this is a d+1 dimensional cone, and this thing here, this profile will be a d-dimensional polytope living in this tangent space. Is it clear for everybody what the profile of the cone is?
Yes.
And this is the random polytope that will describe to us the shape of this cone, right? It captures the shape.
But it's also kind of probability stuff, or you make a quotient with respect to like. So it depends on your point U.
Yeah, it depends on this point U.
So it's kind of random variable again.
Yeah, of course, it's a random variable. This is a random polytope.
Yeah, okay.
And there are two steps of randomness. First of all, you create these random subspaces. Then you select one of these cones at random. And for this random cone, you also choose a random point in the intersection with the sphere. And then you have the random tangent space, and you intersect this random tangent space with your random cone. So, and this gives you a random polytope.
But these
Okay.
two random choices are independent of each other, correct?
Yeah, they are independent of each other. I didn't say this, but yeah, of course, it's independent. But conditionally independent. So given Sn, the U is independent. Yeah. And this profile is able to capture the shape of this cone, because if you know this random polytope, you can reconstruct the cone, right? And the question is, so what Cover and Efron saw, that the expected F vector of this profile converges to the F vector of a cube. And our question was, is it true that these profiles itself as convex bodies maybe also converge to something? And this is indeed the case. And this is our main result. The main result is, first of all, we identify the limit. And at the same time, we also introduced a new method how to prove this, because all the methods we knew were not able to capture this. So as n tends to infinity, n is the number of random hyperplanes. The profiles of these Schläfli random cones rescaled by a factor n. Of course, you have to rescale because these random polytopes, they get smaller and smaller, and you have to blow them up in order to compensate. Okay, you have the right scaling is n, the number of you scale with the number of hyperplanes. And these profiles weakly converge to what is called the typical cell of a stationary and isotropic Poisson hyperplane tessellation in d-dimensional Euclidean space, having a certain intensity, which is maybe not so important. The convergence that we have here is convergence in distribution, and it takes place in the space of compact convex subsets of Rd supplied with the Hausdorff distance. And what is technically in the background of our theorem is a new characterization and a new criterion for weak convergence of random polytopes and cones, which is based on the topological structure on the space of polytopes. And what I would like to explain to you in this talk is, first of all, what is this limiting object? What is this typical cell of this stationary and isotropic Poisson hyperplane tessellation? And also how to prove this weak convergence. So these are the two purposes I have. So how to prove this weak convergence, to give you an idea of what we were doing. But first of all, I would like to explain to you what is this limiting object. It is not the cube, as Cover and Efron claimed. It's a more difficult object, and in fact, it's not a deterministic object. It's a random object as well. And so what is this limiting object? We need to go to the space of hyperplanes in the d-dimensional Euclidean space. And as you know, a hyperplane is always characterized by a unit vector. So a point on the d-1 dimensional unit sphere, which is denoted by p here. And then you look at the hyperplane orthogonal to P at distance T. And this is exactly the hyperplane that I denote by HPT. And the space of hyperplanes carries a natural invariant measure. When you, in this parametrization of hyperplanes, it's just the Lebesgue measure in the distance coordinate and the spherical Lebesgue measure, or the uniform distribution on the unit sphere in all the directions. So that's the invariant measure on the space of hyperplanes. And now you can look at this space and can have a look at the Poisson point process on that space. Well, you have a measure, you have a space, so there's a Poisson point process on that space. And this is called a Poisson hyperplane process with a certain intensity. This is just a Poisson point process on the space of hyperplanes having intensity measure this gamma times, so this is just a constant, times this invariant measure. So this gives you a random collection of hyperplanes. If you look into two disjoint sets of hyperplanes, the number of hyperplanes falling into these sets is independent. And the number of sets falling in, the number of hyperplanes falling into a certain set A follows just a Poisson distribution with parameter gamma times mu of this set. So this is this Poisson point process. And this Poisson point process, so this random collection of hyperplanes, induces a tessellation. So here is a visualization of this tessellation of this Poisson hyperplane process. At least you can see it in a ball here. So it lives in RD, but I can draw you only a picture in a ball. Here you see all these random hyperplanes that belong to this Poisson hyperplane process, and they, of course, cut the space into random polytopes. And now we select one of these polytopes at random, and we do this as follows. For each polytope that you see here, you select a uniform random point. Namely, so we supply each cell of this tessellation with a center, which is denoted by Z of C. In our case, we take Z of C to be a uniform random point in these polytopes. So for each polytope, to each polytope, you attach a blue random point, which is uniformly distributed in each of these polytopes. And now you do the following thing. You look at the realization of this Poisson hyperplane tessellation in a large ball. Then you see a lot of these blue points here, and you select one of them at random and shift the attached polytope to the origin. You shift, maybe you selected this one, and now you shift this blue point to the origin, and you look at the surrounding polytope that you have shifted. And this is called the typical cell of this Poisson hyperplane tessellation. And formally, this typical cell, which is centered around the uniform random point, this is a random polytope, and the distribution of this random polytope is described by this formula here. So this is just the formalization of what I just explained. You take an observation window, and then you select uniformly at random one of these polytopes, regardless of size and shape. And then you shift this polytope that you selected to the origin. And this is exactly the typical cell of this Poisson hyperplane tessellation. And this is the limiting object that you will see. This is the limiting object of this Schläfli random cones. So if you take these n random hyperplanes, choose one cone at random, then you form this profile. This was the thing that happened in the tangent space. And then you take the limit as n tends to infinity up to a rescaling by a factor n. This random polytope will converge in distribution to the typical cell that I just explained to you. And both ends somehow are very classical objects. So these Poisson hyperplane tessellations, they are very well studied, and these are very well-known objects in stochastic geometry. And probably you remember them from Zachar Kabluchko's talk. He was also speaking about these Poisson hyperplane tessellations and the cells attached to these Poisson hyperplane tessellations. On the one hand side, and on the other hand, are just this very classical model of random cones. So this is the object we are dealing with. And the second ingredient is, how do we actually prove, or how can we actually prove that a sequence of random polytopes converges in a certain sense? And for this, we have to go back a little bit to the topological structure of the space of polytopes. First of all, by calligraphic KD, I will denote the space of compact convex subsets of RD. And this space you can supply with the usual Hausdorff topology. Okay. In this space, of course, there is the space of polytopes sitting. This is the subspace of polytopes. And you just take also the Hausdorff topology. Now we even specialize a bit more. We look at the space of calligraphic PDM. This is the subspace of polytopes in RD having exactly m vertices. And the first coordinates of these vertices are supposed to be all different from each other. Okay, this is another space of polytopes. But this space is extremely nice because you can identify this space with the following subset of a Euclidean space. Namely, you look at all at all m tuples of points in Rd, right? Such that all the first coordinates are different, and we say that they are increasing. And yeah, well, you want that they form a polytope, so they should be in convex position, because you want that the resulting polytope has exactly m vertices, so they should be in convex position. So there is a nice identification between the space of polytopes with m vertices whose first coordinates are all different, and this subset of a certain Euclidean space. And we supply this set here with the Euclidean topology. This is a topology you can put your hands on. How can we go further? Well, first, we form two different spaces, namely the space P infinity T tilde. This is just the disjoint union of all these subspaces of Euclidean spaces. And you supply this space with the disjoint union topology. So this is the finest topology, so that all these canonical injections become continuous. And with this disjoint union topology, this becomes a Polish space. This is on the Euclidean side. And on the side of convex bodies, you can also form the union of all these spaces of polytopes, which is a subset of the space of compact subsets supplied with the Hausdorff topology. So these diagrams should illustrate the situation. So here you have the space of convex bodies. In the space of convex bodies, there's sitting the space of polytopes. And here is this space of very special polytopes, namely the disjoint union of all these spaces of polytopes where all the first coordinates of vertices are different. And in each, well, this is just a disjoint union of all these spaces PMD, of polytopes having exactly m vertices. So this plays in the space of convex polytopes. And these spaces here, they can be identified with certain subsets of Euclidean spaces, right? This is exactly what I explained here. So you can identify each of these spaces with a certain Euclidean space, and this union with the disjoint union of certain subsets of Euclidean spaces. And you have identification maps between these spaces, namely they are very easy. If you have points in Euclidean space, you just form the convex hull. And then you go from m tuples of points in Euclidean space to polytopes. These are these canonical identifications that you have between these spaces. And given the topological structures that we put onto these spaces, these identification maps become continuous. This is the first step. And the key is the following lemma, the following observation. If you want to prove convergence weak convergence in the space if you want to prove weak convergence of random polytopes in the space of convex bodies, it is sufficient to prove weak convergence in this space here, namely this disjoint union of these Euclidean spaces. And the reason for this is just the continuous mapping theorem, because all the mappings that you have here, they are continuous. So if you want to prove weak convergence here, it is sufficient to prove weak convergence in this space here. And this space is much more easy because this is just a disjoint union of Euclidean spaces supplied with Euclidean topology. Is this map somehow clear? So this is the key observation that we make, that you can prove weak convergence in this complicated space by proving weak convergence in a certain disjoint union of Euclidean spaces. And this is much easier for us. So, okay,
Christoph,
this is one of the, yeah.
working with the support functions of the polytopes would be much harder.
We have no access to the support functions.
Mhm.
You have no access to this. That's one of, yeah, it's one of the problems. You don't have access to many things.
Mhm.
You have access to the vertices, but, or the generating points of your random polytope, but that's all.
I see.
And usually it's extremely hard to prove weak convergence of random polytopes because you have no idea how to put your hands on these objects. Support functions is not within reach. Okay, so let us recall that we have this disjoint union with the disjoint union topology. And well, each of these spaces is a Euclidean space and it carries a very natural measure, namely the Lebesgue measure. And since this is a disjoint union, you can also glue together all these Lebesgue measures. And this is what we do, namely we denote by mu infinity a measure on this disjoint union such that the restrictions to each of the components is just a Lebesgue measure on RD. No, it's just a Lebesgue measure, sorry. Yeah, it's just a Lebesgue measure. So you have a very natural, you don't have only a very natural topology on that space, you also have a very natural measure on that space. And now you can come up with the following idea. Okay, if you have random variables and you want to prove weak convergence of random variables, let's say real valued random variables. How can you do that? One of these things is you can prove pointwise convergence of densities. So if you have very nice random variables that have a density with respect to Lebesgue measure, it's sufficient to prove convergence of the densities. But this is only possible since you have a topological structure, which allows you to make sense of weak convergence. And you have a measure, you have the structure of a measure, then you can talk about densities. And we now come up with exactly the same idea, but now on the space of polytopes. You have a topological structure, and you have a measurable structure also on that space because you have a measure. And that's exactly what we want to do. So this is called the chevy type lemma for random polytopes. Chevy's lemma is exactly the statement that tells you if you have real valued random variables that have a density with respect to the Lebesgue measure and you want to prove weak convergence, then you can prove pointwise convergence of the densities. And now we lift this idea to this convergence of polytopes. So suppose that you have a sequence of polytopes in RD and of random polytopes in RD and T another random polytope in RD. And let's suppose that these random polytopes are living in our spaces, meaning that they live in the disjoint union of these spaces modulo the identification to the space of polytopes. So all the vertices with probability 1, all the vertices of these polytopes are different and have different first coordinates. And that's exactly what our random polytopes satisfy, the limiting polytopes and the polytopes that we are working with. And now we assume that for each n, the distribution of these polytopes, but now after the identification map that identifies a polytope with its vertex representation in the Euclidean space, we have a density. Suppose that we can compute some kind of density. And that the distribution of the limiting random polytope also has a density with respect to this measure that we introduced on this infinite dimensional space. And suppose that we have pointwise convergence of these densities. Then we have weak convergence of the random polytopes in the space of compact convex subsets with the Hausdorff topology. And this is exactly what you know from convergence of random variables, but now lifted, the whole idea lifted to the space of polytopes. So if we want to prove convergence of random polytopes, you can also try to prove pointwise convergence of densities. And this is possible because on this space of polytopes, or on the subspace of polytopes, which is sufficiently rich for us, where you have a topological structure and the structure of a measure. And these are the two ingredients that we would like to bring together. And this is this chevy type lemma. The proof is very easy. Maybe I can show it to you. Well, this is just a lemma that I have shown to you before. This is just a direct corollary of the continuous mapping theorem. And what we need to prove is now weak convergence of these random polytopes. So what we have to take is a bounded continuous function on the space of vertex representations of polytopes and prove that the expectation of h of Tn converges to the expectation of h of t. This is just definition of weak convergence. And this is extremely easy once you have all the notation and notions together. So what we have to prove is that the difference here converges to 0. So the integral of h with respect to the distribution of Tn converges to the integral of h with respect to the distribution of t. Well, but Tn and t, they have densities with respect to this measure mu infinity. So you just use here that you have densities. Now you use that h is bounded and you use the triangle inequality, and then you arrive here at this last line. But by assumption, well, you have pointwise convergence of these densities, and then this converges to 0 by Chevy's lemma. And this is all you need. So the next thing is, well, how can we use this Chevy type lemma for our purposes? And for this, we have to introduce some more random cones. Let us briefly recall what we did. So we have this Schläfli random cone. How did this Schläfli random cone arise? So you have all your random hyperplanes. You select one random cone uniformly at random among the collection of all random cones. This is the first random cone, and this is the random cone we are interested in. But there are more random cones we can look at. Namely, you can look at the random cone containing the south pole of the sphere. So here's the south pole of the sphere, and here's the random cone that contains the south pole. Let us call this the south pole cone, and this is denoted by Sn minus E. Okay, this is this green cone that you see here. Now we do something different. We now consider just the upper half sphere, the d-dimensional upper half sphere. This is the upper half sphere here. You take IID uniform random points on the upper half sphere. These are the red points that you see here. And you just look at the cone generated by these random points. So this is just the positive hull of these random points. This is the random cone Rn. And you can, at the same time, also look at the polar of this cone. This is the red cone that you will see here. And these are the four random cones that are extremely important for us because these random cones are related to each other as follows. The red cone here has the same distribution as the South Pole cone that you see here in the picture on the left-hand side. So the dual of this positive hull of the random points on the half sphere has the same distribution as the random cone containing the South Pole in the model on the left-hand side. This is the first observation. The second observation is the South Pole cone is the size-biased version of this Schläfli random cone here, meaning exactly what is written here. So this is, you can imagine this as follows. So to each cone, you can associate its solid angle, right? It's just the opening angle of this cone. It's the probability that a Gaussian random vector in the linear hull of this random cone of a cone belongs to this cone. This is just the opening angle of a cone. This is called the solid angle of a cone. It's a number between 0 and 1. And the South Pole cone up to a random rotation can also be thought of as follows. The Schläfli cone was selected uniformly at random among these cones. The South Pole cone can be thought of as a random cone that is selected according to the weights given by the solid angles. So you select proportional to the solid angle. So a cone with a larger solid angle has a higher chance of being selected compared to a cone with a small solid angle. And up to a random rotation, the South Pole cone is exactly a random cone selected according to these weights, weighted according to solid angle. And these two observations here give you a link between all these random cones. So first of all, the Schläfli random cone, this is the random cone of interest for us, is linked to the South Pole cone, and the South Pole cone is linked to this cone by polarity to a convex hull, to a spherical convex hull or the positive hull of uniform random points on a half sphere. And uniform points on a half sphere, this is a model which has been studied in the literature. And going back from the green cone to the red cone, from the red cone to this green cone, and from this green cone to the blue cone, you can actually derive properties of the Schläfli random cone from the cones Rn. So the cones generated by uniform random points on a half sphere. And this is exactly the model we should study, and this is the model we have studied in the past. Namely, we do the following thing. Again, you look at these random cones Rn now. These are the random cones generated by uniform random points on a half sphere. You intersect these cones by the tangent space at the North Pole. This gives you a random polytope in this tangent space. And now you take your favorite isometry identifying this tangent space with Rd. So this gives then you a random polytope in Rd. This is a random polytope which gets bigger and bigger because the opening angle of this cone gets bigger and bigger. But if you rescale with a factor 1/n, this converges. This sequence of random polytopes converge. Namely, the sequence of these random polytopes, they converge, they weakly converge to the convex hull of a Poisson point process in Rd. It's a Poisson point process in Rd minus the origin, and its intensity measure has exactly this density with respect to the Lebesgue measure. And to give you an impression of how these limiting random polytopes look like, I have prepared some simulations for you. So this is in dimension 2, this is in dimension 3. So what you will see here is there is the origin. Around the origin, there are infinitely many points in any small neighborhood. But in the complement of any small ball around the origin, there will be only finitely many points. That's why there are so many points here accumulating around the origin. This is clear because this is not, this function is not integrable around the origin. So there must be infinitely many points here. But outside of any ball of any positive radius, there are only finitely many points. So the convex hull of this Poisson point process is in fact a polytope. And here you will see a realization in dimension 2. So this is this random polygon. And here there's the origin somewhere here inside. So again, there are infinite many points accumulating around the origin, but the convex hull of this Poisson point process again is a random polytope. And this is exactly the limit of the profiles of these random cones. And this is something we have seen earlier in the paper together with Saka Kabluchko, Sasha Marinic, and Daniel Temeshwar that has appeared in 2019. And now, at least philosophically, you can complete the picture. We want to know something about the random Schläfli cones Sn. They are the size d-biased versions of the South Pole cones. And the South Pole cones are equal in distribution of the duals of these cones generated by points on a half sphere. And now you have to go back all the things. So why is now the result about the random Schläfli cones plausible? Because of the following thing: the duals of these Poisson, of these convex hulls of these Poisson point processes, they have the same distribution of the so-called zero cell of the stationary and isotropic Poisson hyperplane tessellation. The zero cell is just the cell of this tessellation containing the origin, but the zero cell is the sized biased version of the typical cell, or equivalently, the typical cell is the sized d-biased version of the zero cell. So up to polarity and size biasing and de-biasing, you have the following diagram. We want to say something about Sn. You do size biasing, you end up with these South Pole cones. They are equal in distribution to the dual or the polars of these half space cones, half sphere cones. So you have this polarity and then you are at the half sphere cones. For these half sphere cones, we know already something, namely the convergence. This is this arrow here. And then you go back, polarity, equality in distribution. And then instead of size biasing, you have to do size de-biasing. And this gives you precisely our main result. This is the way we prove this. And since we have some more minutes, I would like to explain to you how this arrow works, using the chevy type lemma that I have explained some minutes ago. So the thing is, now we have to compute the densities of these random polytopes here on the left hand and on the right hand side. So let us compute these densities. So again, let us recall the setup. So you have uniform random points on the upper half sphere, and you look at the cone generated by that. So this is the picture. You have the half sphere, you have the points uniformly distributed here, and you look at the cone. This is the cone Rn. Good. And well, just by brute force computation, if you do the radial projection, so you just project all the points to this tangent space here. Well, you project just here. This gives you points, random points, and just by brute force computation, you can compute the density of these points. The density of these points is exactly this here. This is the density of these points, which means that if you look at the profiles of the cone Rn, this is exactly the convex hull of random points, IID random points having this density. And well, we want to have the rescaled cones, the rescaled profile, so you have to rescale as well. And now let us compute the density on this space. This was this disjoint union of subsets of Euclidean space. Let us compute the densities of these random polytopes. The density looks as follows. This is the density I claim. So we have these endpoints, and you want to have the density on the space of polytopes having m vertices. So first of all, you have to select among these endpoints the m vertices. How many choices do you have? Well, n choose m choices. This is the first factor here. Well, if you permute the labels of these m points, this doesn't change the convex hull. So you have exactly m permutations, and well, this is the second factor that appears here. Next, you have to choose the vertices among the density they are distributed. This is exactly the first product here. This is the density of the vertices. And since we have a rescaling by a factor n to the -1, there's some n appearing here, some factor n appearing here. And then you have to ensure that all the remaining n minus m points are in the convex hull of the vertices that we have selected. The probability for this is, or the density for this is exactly the integral over the convex hull of your vertices of the density. And again, you have some rescaling here because you rescale the profiles. This is the density of these random polytopes. So this density is this is nothing very abstract, but this is something you really can put your hands on. Let's try to compute a little bit with these densities. First of all, the m factorial cancels here. This is this. Then this density has some constant factor that you pull out. Then you plug in just the definition of the density. Well, and here you have the integral over the convex hull, which is the same as 1 minus integral over the complement of the convex hull. And you also plug in the density here. So nothing happened here. Next, well, you take out from the bracket the factor n. And you do this m times, because this is an m-fold product. This gives rise to a 1 over n to the m. Then there is some constant factor that we just copied. Here we took out this factor n. And we did the same here. We took out the factor n from the density. This is why there's a 1 over n here. But now this is very nice because, well, this fraction here also, this behaves like n to the m, which cancels very nicely with this n to the m. So this goes to 1. 1 over n squared goes to 0, sorry. Here, this 1 over n squared goes to 0. And here you have 1 minus a constant divided by n to the power n minus m. And since m is constant, this converges as well, right? So this just converges to the constant that we copy. Here, the density, this m-fold product. And of course, this goes to an exponential expression, exponential minus constant times this integral. So this is the limit of these densities on the space of polytopes. And now we have to verify that this is exactly the limiting density. So what is the limiting object? Let us recall. This was a Poisson point process, pi was a Poisson point process on our d minus origin. And the density function was this one here. And now let us compute the density of the convex hull on this fancy space. So again, you want that the points x1 to xm are the vertices of the convex hull. Well, the density of each of these points is, well, what it is. This is this m-fold product. And then you want that all the other points are contained in the convex hull of these points that you have chosen here, or equivalently that in the complement there are no points. But since this is a Poisson point process, you can compute this probability. This is exponential, right? This is exponential of minus integral over, well, this set of the density. But this is exactly what it is. Now you can put here the density, and well, this is exactly the same expression that we have seen on the last slide as a limit. And now we have proved that these densities converge pointwise, and we can apply our chevy type lemma to conclude weak convergence of the random polytopes on this fancy space, which implies weak convergence of the random polytopes with respect to Hausdorff distance. And that's how you prove, or this is one of the possibilities to prove weak convergence of random polytopes. And in fact, it was the only possibility that we are aware of to prove weak convergence of random polytopes of the kind we have. So just as a take-home message, well, these Schläfli cones, these are nice objects. And the profiles of these Schläfli cones, they converge if you rescale them appropriately to a very, very classical objects from stochastic geometry, namely the typical cell of a stationary and isotropic Poisson hyperplane tessellation with a certain intensity. Okay. And now we can come back to this cover and Efron statement, namely that loosely speaking, the cross section of these Schläfli cones, they are cubes. And we have to say, no, they are not quite correct. These cross sections are not cubes. They are typical cells of a stationary and isotropic Poisson hyperplane tessellation. But in a certain sense, they were still right because the effector, the expected effector of the typical stationary and isotropic Poisson hyperplane tessellation is the same. Oh, there should be no expectation here, is the same as the effector of a cube. So regarding combinatorial parameters, cover and Efron were right, but they were not right when the shape of the random polytopes is considered. If you want to know more, then there are two papers I would like to recommend. Namely, there is one paper about cones generated by random points on half spheres and convex hulls of Poisson point processes. This is the model where, as the title suggests, and we looked at these random cones generated by points on a half sphere. And there is this second paper where we developed this new approach to weak convergence of random points, random cones and polytopes. And as an application, we have these Schläfli random cones, the convergence of these Schläfli random cones. And yeah, I think my time is over. And well, I would like to thank you for your attention. And I would be very happy if there are many more problems that one can treat with our technique. And maybe you have an idea how to use it. Thank you. And thanks for your attention.
Thank you very much, Christoph. Are there any questions?
Yeah, but kind of without going to details, intuitively, you're like, what's happening on the sphere? Like if you look on a small scale, it's like almost the same as what happens on the
right
on the Euclidean space. So it's just some small curvature, and essentially you prove that curvature does not important.
Right. This is absolutely correct. Yeah. This is absolutely correct. To fill all the details is very messy, but yeah.
Yeah, so it's kind of very natural kind of statement.
Yeah, it's very net. It's very natural.
Very hard, very non-trivial proof.
Yeah, especially that you have to develop a method how to attack weak convergence of these polytopes, because this was the most technical part. Yeah. But on an intuitive level, that is absolutely true. On a small scale, you will neglect curvature, and what happens is what happens in Euclidean space. Absolutely.
Yeah. Probably for physicists, that would be the proof.
Yeah, unfortunately, the proof is much more complicated.
Yeah, unfortunately.
Yeah.
Christoph, when you study the model on the half sphere, is the half sphere special, or can you study other angles as well?
You can study other angles as well, but then it becomes boring. The only interesting case is the half sphere case.
I see. Okay.
Yeah. Because if you, it's the only interesting case. So, I mean, there are some intermediate cases that you can try to study. As soon as you study a spherical convex body, then you are back basically to the Euclidean setup. But what you can do is to study, well, this, but how you describe this, like a loon, like a banana on the sphere. Something like this can also be studied, but this is already very close to the Euclidean setup. The really interesting case is the half sphere case.
Okay. Any other questions? If not, let's thank Christoph again for the very interesting talk. And